Okay, so this is lesson 10.4, and what it is that we're going to look at some forces that are vectors. So our forces are going to be written in the form AI plus BJ, and that'll be in newtons. Then we're going to be using that with mass, which of course will be measured in kilograms. And then we're going to have some accelerations to go with it, because we're going to be using the formula force equals mass times acceleration, just like we've been doing in all the other lessons in the unit. Except this time it will be vector acceleration. So if the forces are vectors, where they're I and j components, then the acceleration as well must also be a vector. So this will be sum of a constant, so say it could be ci plus dj, but an important part will be that it's meters per second squared, again, like all the accelerations you've seen. So it's going to work exactly the same with force equals mass times acceleration, right? The most important formula there is in mechanics for us, but they're just going to be with vector quantities. So let's start off by having a little look at example 8 and see how that applies to that. So example 8 just starts off by saying that I represents the unit vector due east and j is the one due north. So what we're going to do with that is we are going to just write down what the question tells us. So it tells us that the force is 3I plus 8j, and that the mass is 0.5 kilograms. So all we're going to do is we're going to do F equals ma, and then we're going to substitute in. So I will use the column vector notation again because I think it's easier in this scenario. So it's 3, 8 equals 0.5 times a, and remember a will be a vector as well. So all we're going to do to solve that equation is going to times both sides by 2, right, to get rid of the 0.5, and that will tell you that your acceleration a is going to be equal to 6/16. And if we want to write this, we can write this using the original I and j notation, so it'll be 6i plus 16j, and the acceleration will be meters per second squared. So that's telling you the direction of the acceleration with the I component and the j component. And that's part A. For part B, it asks for the magnitude and the bearing of the acceleration of the particle. So the first thing I'm going to do is I'm going to draw a picture like I did previously in lesson 10.2. It's going to be very, very similar. Right, so we've got 6i, so that's off to the right, and positive 16j, so it'll be up. So it's going to look something along these lines, where it doesn't have to be to scale, just a rough sketch. So we've got 6i and 16j. And then if we're looking for the magnitude and the bearing, well, we're going directly there. So the pink arrow is representing my magnitude, and we're going to use Pythagoras to work out what it is. So 6 squared plus 16 squared, all square rooted. Right, and because it's mechanics, I'm going to give my answer to 3 significant figures. So I've got it on my calculator, and that turns out to be 17.1. And then because it's acceleration, it's still going to be meters per second squared. Right, so that's the magnitude of the acceleration of the particle. If I want to find the bearing, as always with a bearing, I'm going to have to put my north line in, and I'm looking for this angle here, but in order to get that, I'm going to get the angle inside the triangle. So if we call that theta, we can say that tan theta equals 16/6. So theta is tan inverse of that. So that gives you theta equals 16 divided by 6, which is 69.4. Of course, that is not the bearing, that is just the angle inside the triangle. Our bearing is measured from north clockwise. So our bearing, I'll pop it here. So our bearing is going to be equal to 90 minus 69.4, which gives you 20.6. But of course, because it's a bearing and it's only 2 digits at the start, we have to pop a 0 in at the front. Okay, so that's our bearing of 20.6 degrees and a magnitude of 17.1.